Imagine you're rock climbing and you need a rope that's strong and reliable. So you reach into your pack and you pull out this, a tangled mess. Unpredictable, messy, and you pull on one end and it gets worse. That's exactly what happens when your code has accidental coupling. In this video, we'll explore intentional coupling, or how to design dependencies that are strong where they need to be and flexible everywhere else. I'll show you how to spot bad coupling and fix it, and use techniques like dependency injection to keep your code clean, adaptable, and testable. So if you've ever changed one line of code and broken 5 unrelated features, then this video is for you. So let's dive in. Hello world, I'm David Scott Bernstein and welcome to The Passionate Programmer. In this video, we're going to be talking about coupling, one of the most overlooked factors in software design. We often hear about tight coupling and loose coupling, and one is bad and one is good. I always forget which one is which. I much prefer the terms intentional coupling and unintentional or accidental coupling, because then it's really clear which one is the good one and which one is the bad one. I want to point out, we are not striving for no coupling in our system. A system that has no coupling is a system that does nothing. We want coupling where we intend it to be, but we just don't want any unintentional coupling. Some dependencies are essential and they reflect the core nature of your domain. Those are good. But other dependencies sneak in unintentionally and make code brittle and hard to change. Intentional coupling reflects the nature of the problem that we're solving. Accidental coupling provides unnecessary entanglements. You may wonder, how does bad coupling show up in our systems? And the answer to that question is that it's a second-order effect. When we have poorly cohesive code, it means that our entities, our objects, are dealing with multiple responsibilities. So there's multiple different reasons to couple to them. And so we get poor coupling. Same thing with redundancy. When we have redundancy all over the place, we got to couple to multiple things if we have dependencies on them. So coupling is a second-order effect. It is the result of other poor code qualities that are not present in your code. Poor coupling makes testing, debugging, and refactoring a painful chore. Code with excessive coupling is often harder to reuse. The goal is not zero coupling. It's deliberate, meaningful dependencies that reflect the nature of the problem we're solving. We want to minimize dependencies that don't add value. When you understand coupling and all of the little nuances around it, you'll become a much better architect and problem solver. We need to recognize that there are 2 kinds of coupling in software design. I call them domain coupling and implementation coupling. Domain coupling is the kind of coupling that's required by the domain. It reflects the nature of the problem that we're solving, and it's good. Implementation coupling is how we implement the domain model on a system. We are dealing with a computer system, so we have to save data in files and display things on the screen, and that is another form of coupling, the coupling that's part of manifesting the business rules, the domain model, in a computer system. Oftentimes, the implementation coupling that we have gives us options. There's options of other ways of doing it. But the domain coupling, there's only one way. There's only one set of business rules that the business wants us to follow. But we can implement those business rules in many different ways. So seeing the distinction between domain coupling and implementation coupling can often be freeing because it can show you where points of leverage are and where things have to stay the same. Some relationships are foundational to the business logic. For example, an order has to have a line item. Otherwise, it makes no sense. If these relationships don't exist, the system would not work. So we have to have them. So this is good coupling. Poor coupling happens when classes depend on something that is implemented rather than what it does. So we have implementation coupling when we depend on implementation details rather than depending on the outcome of what that implementation creates or does. For example, an order could depend on a specific database structure instead of on an abstraction. This is a challenge because if we want to swap out databases for some reason, we would have a lot of reworking to do. Where if it was dependent upon the abstraction, we would just modify the abstraction to the new database and boom, everything would work. That's the idea. Implementation details should be hidden behind interfaces or services. And this makes our code much more robust. Coupling often starts small. You add a method call here, a shared dependency there, and suddenly the system is a web of entangled dependencies. Ever struggle to explain why some code just feels better than others? There's a reason for it. Great code follows certain qualities that make it easier to work with. That's why I created the Clean Code Quality Checklist. This is a simple tool to help you spot great code and identify problem areas in your own work. It breaks down what makes code cohesive, loosely coupled, encapsulated, assertive, and non-redundant, so you can instantly see where improvements are needed. And the best part is, you can download it for free as part of my Clean Code Toolkit. The link is in the description. Check it out. I think you'll find it valuable. Here's some signs that you have poor coupling in your system. Probably the biggest, most obvious sign that we can recognize is global variables. Global variables are bad for a couple of reasons. One is because we can couple to it anywhere, and there's no guarantee that we won't couple to it. So because of that, it introduces a lot of unknowns into our system. But global variables are bad for other reasons as well. The reason that I hate globals is that they hide my dependencies, and they force you to read all of my code. See, globals like read-write singletons or other kinds of globals can oftentimes hide a key dependency in the code that does not get broadcast in the method signature. All of my dependencies should be in my method signature. So you can just read my header file or read my method signatures and not have to read every line of code. But when I hide dependencies using globals, I'm forcing you to read all of my code to be able to see where my dependencies are. Not good. So that's another reason why I don't like global variables. Deeply nested dependencies are another problem. When we change one module, it can ripple through the entire hierarchy, which can be a big issue. Direct dependencies on external services. When we code concretely to external services, it makes it impossible to swap those services out for testing. Spaghetti inheritance is another big issue. When we create deep inheritance hierarchies, changing one class can affect all the classes downstream. And when we hard code class references, it prevents flexibility in our design and oftentimes impedes testability as well. So how do we deal with that? How do we deal with dependencies that we want to use, but we don't want to create? And what we do is we inject them. And that's what dependency injection is. You've probably heard of or used dependency injection frameworks like Spring. This is just doing it manually, doing it ourselves. So if we want to use a service, instead of newing it up and then calling the service, we ask another entity to new it up for us. And then the entity passes us that object that it newed up and we can use it. The entity that newed up the object for us could pass us an interface to the object instead, or a superclass, like an abstract class, that it conforms to. And so we don't need to know what the derived type is. And that is the key to polymorphism, the key to substituting types in the future. It gives us the flexibility to add new types that conform to the same interface in the future without breaking any of our callers. That, I think, is like the one big trick that object-oriented programming does. And it's incredibly valuable. So we want to use it. We want to take advantage of it. This is what I think, inheritance is really for giving me the ability to do polymorphism. I don't really like to use inheritance to specialize because I find that it can create very poor code quality, as we'll see in a future video. Here's an example. Here, order services is tightly coupled to the database. If we wanted to swap out the database or write tests against it, we're stuck. We have to involve the database in our tests. But here it is after refactoring. Now we're dependent not on the database, but a data access object, or DAO. The DAO points to the database, but we can make the DAO point to a fake instead for testing. Now order service depends on an abstraction, data access object, instead of the concrete class. This means that we can easily substitute different implementations, making testing and maintenance far simpler. Ever struggle to explain why some code just feels better than others? There's a reason for it. Great code follows certain qualities that make it easier to work with. That's why I created the Clean Code Quality Checklist. This is a simple tool to help you spot great code and identify problem areas in your own work. It breaks down what makes code cohesive, loosely coupled, encapsulated, assertive, and non-redundant, so you can instantly see where improvements are needed. And the best part is, you can download it for free as part of my Clean Code Toolkit. The link is in the description. Check it out. I think you'll find it valuable. So here are some key takeaways. Use interfaces or abstract classes. Apply dependency injection to increase testability. Minimize knowledge of concrete implementations. That reduces the ripple effect when changing code. A company that I worked with had a legacy system where every service talked directly to the database. Every database update broke several different features in the system. We introduced the repository layer using dependency injection, which separated the business logic from the data storage. What was the result? Bugs dropped significantly. It was like 70% bugs dropped, and development speed nearly doubled. We work in code all the time, so having a clean environment to work from is incredibly valuable, and it means that our bottom line gets better. Intentional coupling is great, but there's another critical factor: encapsulation. Hiding unnecessary details and keeping dependencies to a minimum. In the next video, we're going to break down encapsulation, why it's essential for scalability, and how to apply it effectively in real-world scenarios. So if you want to make code more modular, more secure, and more straightforward to change, then watch this next video. Subscribe and hit the bell icon so you don't miss any new videos when they come out. Until then, happy coding.